In this video, we're going to solve 6 circular motion problems. The first problem we're going to look at is a ball on a string that's swung vertically. So this student right here is swinging this ball on a string, and we want to find the minimum speed at the highest point. And to do that, we're going to first identify our system, which is this ball right here, and then we're going to draw the force diagram. So we know that there is gravitational force, mg, and then from the string, there is a tension force also downward. We're going to then select our coordinate system. Typically for circular motion, the direction towards the center will be our positive direction. So that's going to be, in this case, it's going to be down. Okay, and then next we're going to apply our centripetal force equation. And I like to label centripetal force with this net force because sometimes there's more than one forces, and this is reminding me that this is the sum of the forces, the net force. And it's equal to mv squared over r. M is mass, v is speed, and then r is the radius of the circle. When we're looking for the minimum speed, that's going to be when we're going to set the t to 0. So if we set the t to 0, we just end up with mg equal to mv squared over r. We could pull it with a greater force, but then it would go at a greater speed, and we're looking just for the minimum speed. So we're setting that t to tension force to 0. We're looking for the velocity here, so I'm going to move the velocity, isolate the velocity, and then the m's, notice the m's cancel out, and then we get v squared equals gr. And then we get that v is equal to square root gr. Okay, so this is the minimum speed to get all the way through the circle. Now we're going to look at a problem where the ball is at the bottom of the circle. And now the ball is at the bottom of the circle, and we want to find the tension on the string at the bottom when the speed is double of part A. So just a reminder, in part A, we found that the velocity, I'll call this v1, that from part A, that v1 is equal to square root of gr. Okay, so now we want to find what is the tension of the string at the bottom of the speed. So once again, I'm going to draw the force diagram at the bottom, and we have gravity force, which I will label mg, and then we have tension force. And notice that the tension force is going to be longer. When an object is moving in a circle, you need to have a net force towards the center. And so I'm going to label the TB because we're at the bottom. So this is a tension force at the bottom. And then we have mg here pointing down. Okay, so we know that the speed is going to be double. So the speed in this problem right here, this v right here, is going to be double to v1, which is going to be 2 square root of gr. Once again, I'm going to set up my centripetal force equation. Net force centripetal equals mv squared over r. Remember that centripetal force is not another force like gravity or tension. This is a role that any force can play. In this case, it's played by the net force of the tension force and the gravity force. So we're going to take TB, the tension at the bottom, minus mg, the weight, is equal to mv squared. Now v squared is this 2 square root gr. So it's going to be 2 square root gr, and that's all squared, divided by r. Okay, so let's square that. So we have m, it's going to become 4 gr over r. And you'll notice that one of the r's will cancel out, okay? And then if we want to isolate tb, we're going to isolate tb. We get tb is equal to mg, and it's going to be plus 4 mg. And so we get a total of 5 mg. All right, so what does this tell us? So this is telling us that at the bottom, if we were to double the speed from part A, at the bottom of the swing, it will have a tension force of 5 times the mass times g. Now let's take a look at a problem, circular motion problem, where a car is going in a circular path. And the question is, what is the minimum coefficient of static friction to prevent the car from slipping? So if there's no static friction, then this car is going to keep on going in a straight line. But because there is friction, this car is able to go around this turn here. So we're going to first draw a force diagram. And so here's my road. And this is going to be a picture of the car from the back. So imagine if you were driving behind this car, and if you're back here, this is what you see from the back. So we know that there's mg of the car, the force of gravity of the car. There's also normal force. I'm going to call that capital N. And then there's going to be a static friction towards the center of the circle. So this static friction is what's causing it is playing the role of the centripetal force, causing the car to be able to go in a circle. Next, I'm going to write out the centripetal force equation, and force centripetal equals mv squared over r. Okay, so what is playing the role of the centripetal force here is the static friction, and that is equal to mv squared over r. Okay, so static friction, the equation for static friction is mu n, and set that equal to mv squared over r. Okay, now n is equal to mg. The reason we know that is because it's that accelerating up or down. So those two forces are balanced. So I can substitute mg. For n, and that's mv squared over r. We can cancel out the m's, and then now we're looking for a coefficient of friction, the coefficient of static friction, which is going to be equal to v squared, and I'm going to move the g over to the other side, and I get gr. All right, so this is the minimum coefficient of static friction to be able to prevent the car from slipping. Now we're going to take a look at an orbital problem. So we're going to, here we have the sun and a planet, and we want to find the orbital speed of the planet. So what is the speed at which the planet needs to have in order to move in a circular path? If the planet is going too fast, then it's not going to be circular. It might be a kind of an oval path. But if it's not going fast enough, it could circle in and then fall into the sun. So we want this to be a circular path, and we want to find what that speed would be. So the force that's playing the role of centripetal force here is Fg. So let me just do a quick force diagram here. So it's going this way, and the Fg, or we could call it I'll just call it the Fg, is going to be towards the center. Okay, and so we'll start with the net force centripetal equation is equal to mv squared over r, and the force that's playing the role of the centripetal force here is gravitational force. Now we can use mg when we're like on a planet and we know what g is, but here these are large masses and they're far apart, and so what we're going to use is the universal law of gravitation, which is big G m1 m2 divided by d squared. Now the two m's are going to be the mass of the sun and the mass of the planet. And then the distance is going to be the r of the circle. So I'm going to just say r here. So that's just the distance between the planet and the sun, and that's going to be squared. Okay, and then we're going to set that equal to mv squared over r. Okay, so what you notice is that one of the m's will cancel out, okay, and one of the r's will cancel out, and that leaves us with big G, the gravitational constant, times m, this is the mass of the sun, divided by r, equal to v squared. And then if we solve for v, we get the square root of big G, big M over r. And this equation also works for, like, if you want to find what the orbital speed of a satellite around a planet, this would also work as well. So basically, what is the speed you would need to maintain that circular motion? And notice that it does not depend on the mass of the object that's going in a circle. So in this case, this is the planet going in a circle. So the planet's mass has no effect on the speed it needs to go around in a circular orbit. Now let's take a look at a problem with a car that is going around a banked turn. So we want to find the angle at which no friction is required for a car to navigate a curve. This is a banked turn here, and So if there was no friction, what is the angle required? We're going to first start with a force diagram, and I'm going to just go ahead and redraw this down here so it's a little bit cleaner. Okay. And let's say this is the car right here. Okay. And we have, first we have mg, so do that mg right here. Okay. And then we also have the normal force. Here's the normal force. Okay, so we're going to break this into components. This can be broken down into components, and I'm going to make, this is the vertical component. Here's our horizontal component. Our theta over here is our angle here. This angle right here is going to be the same as this angle right here. They will have the same angle. Okay, so this is going to be, because this is opposite, this will be n sine theta, okay? And then this is adjacent, so this will be n cosine theta, right? And once again, we're going to set up our centripetal force equation, which is net force centripetal equals mv squared over r, okay? So we know that so this is going to circle this way, okay? And so toward the center, it's going to be in this direction. That's going to be towards the center right here. So the force that's towards the center is going to be n sine theta. That is the only force. That force, that n sine theta, is playing the role of centripetal force. And that is equal to mv squared over r. Okay, so we're going to try to isolate n here, and we get mv squared over r sine theta. Okay, so we're looking for an angle, but we don't know what the normal force is. So I need to get rid of that normal force. So now let's take a look at this problem vertically. So we saw it horizontally, but vertically, we're going to use Newton's second law. So net force in the y direction equals ma. Okay, so I'm going to make right positive and up positive. So right is positive and up is positive. So we have n cosine, so all the forces in the positive direction minus all the forces in the negative direction, or you could say all the force up, n cosine theta minus all the forces down, which is mg, is equal to, and it's not accelerating up or down, so that's going to be 0. Okay. So next, we're going to isolate n and maybe try to get rid of this n here. And we get, move this over, we get mg, and then divided by cosine theta. Okay, I'm going to set these equal to each other because they're both equal to n, so I can do that. So mv squared divided by r sine theta is equal to mg over cosine theta. Okay, and then you'll notice that the m's cancel out, which is really nice. And then we're going to move the sign over. I'm going to move the sign over and move the g over. Okay, so on the left-hand side, we have v squared over gr. On the right side, we have sine theta over cosine theta. Okay, now sine theta over cosine theta is just tan theta. So tan theta is equal to v squared over gr. Okay, so this is the angle at which, if there's no friction, that would be required in order for the car to navigate the curve. Next, we're going to look at a car that is going down through a dip, and we want to find the normal force at the bottom of the hill traveling at velocity v. So once again, I'm going to start with a force diagram. Here's my car. And we have mg going down, my gravity force, and my normal force is going to be up. Now, the normal force is going to be greater because the center of the circle is above, so it's going to have a greater force. You need to have a net force towards the center, and this car is moving to the left. Okay, so now we're going to set up our centripetal force equation. Centripetal force is equal to mv squared over r. the forces toward the center, which is N, minus the forces away from the center, mg, is equal to mv squared over r. Okay. So now I'm going to solve for N, and N is equal to mg plus mv squared over r. So this makes sense if you look at the situation. This makes sense because the normal force has to be greater than mg in order for it to go in the circular path because the center of the circle is above. And in this case, it's going to be plus mv squared over r. That gives it the additional amount that it needs, so such that the net force is towards the center to cause it to go in this circular path. Now let's take a look at the car going over a hill, and we want to find the normal force at the top of the hill traveling at velocity v. Okay, so here's my force diagram right here, and we have mg, and this time the normal force is going to be less. It's going to be less because the center of the circle is below. And once again, we'll start with our centripetal force equation equal to mv squared over r. And because the center is down, we're going to start with mg minus the normal force equals mv squared over r. And then n, I'm going to move this to the other side. We get mg minus mv squared divided by r. And so this should make sense too, because this means that the normal force is less than mg. And that's the case because the center of the circle is below. All right, now we're going to take a look at a conical pendulum. And so we have this toy plane connected to a string, and this plane is going in a circle. It's a conical pendulum because it sweeps out a cone shape. And we want to find out what is the period. How long, by period, we mean how long does it take for this plane to go in one complete circle? All right, so we're going to start with a force diagram. And we're going to start with mg going down. And then we have tension going this way. And those are the only two forces. I'm going to set up my positive direction towards the right and up. Okay, so those are going to be my positive directions. And I'm going to break my tension into components because they're not on my coordinate axes. So we're going to have a component going up and a component going to the right. The component going to the right, because this is theta, so this angle right here will also be theta. Okay, so you can kind of convince yourself. So if I have a line right here, and this is coming through, right? This is coming through, right? So this is theta. This is also going to be theta as well. Okay, and then so now I'd like to write these in terms of trig functions. So this is going to be t sine theta, and then I'm actually going to use ft here because we have tension, and that's we got period, which is t, so that gets confusing. So this will be ft sine, and this will be sine theta, and this will be ft cosine theta. Though what reason I know that is because this is adjacent and this is opposite. Okay, and then let's go and call this ft right here. All right. So now we're going to analyze this first vertically. I'm going to just analyze this vertically. Net force in the y direction equals ma. So using Newton's second law, we can see that ft cosine theta is equal to mg, right? These have to be equal to mg, Well, we could do minus mg equals 0, right? Because no acceleration, and so therefore ft cosine theta equals mg. Okay. Now let's take a look at it horizontally here, and we are going to use our centripetal force equation equal to mv squared over r. So what force is playing the role of centripetal force? It is going to be ft sine theta. So not tension, but a component of tension. So we have ft sine theta is equal to mv squared over r. Okay, so now I'm going to come back here and isolate ft, and we're going to do a substitution. So ft is mg over cosine theta. I'm going to do a substitution here. So I'm going to substitute mg over cosine theta into sine theta, okay, into ft and times sine theta. And that is going to be equal to mv squared over r. Notice that the m cancels out, okay? So the mass of the plane does not factor into this period here. And then we have sine theta over cosine, so that's tangent, right? Sine theta over cosine theta equals tangent theta. So g sine theta is equal to v squared over r. Okay, so now we're trying to find the period, but how are we going to get the period? Well, if you go in a circle, the speed is equal to distance over time. So in a circle, it'd be the circumference over the time to make one complete circle. We have a name for that. We'll call that the period. So the period is equal to, so the velocity is 2 pi over r. So we can substitute that over here. Go back over here and substitute that. So we have g tan theta equals to, and we have 2 pi r over t, and that whole thing is going to be squared. That whole thing is going to be squared. Okay, and we also still have a 1 over r here. Okay. So now we're going to square all of that. So g tan theta equal to 4 pi squared r squared over t over r. You'll notice that the one of the r's will cancel out, so there's a canceled out there. Okay, and what are we looking for? We're looking for t. So if we isolate t by itself, we get 4 pi squared r over g. Okay, now over here, this t is actually squared. I'm going to square that, and this is actually squared. And then so if we just square root both sides, we get t equals to 2 pi, and then we're going to square root. Let's see here. I got a tangent here. Yep, there's a tangent that I moved over, tangent theta right there. Okay, and then so we end up with square root of r over g tan theta. Okay, so let me write that over here. So what we end up here is t is equal to 2 pi square root r over g tan theta. Okay, so what is that telling us? So that's telling us the amount of time it takes for this plane to make one complete circle. Okay, and so it's affected by how big the circle is, the radius of the circle, and also the angle. But notice one thing it does not depend on is the mass of the plane. That does not affect how long it takes for this plane to make one complete circle.